This is Mr. Martin. These are the video notes for section 6.3, Vectors in a Plane. This is day 2, actually, and this is for Precalculus Honors. So we're going to be talking about direction angles today, and we're going to be doing some application problems, and we're going to look at some other important things in the notes as well, and I'll point those out as we go along. But the first one that we want to look at is the direction angle. So if we look at the diagram here, we can see theta, and here's our vector, and we can see the magnitude is labeled, and the direction angle is just the angle from the positive x-axis in a positive direction. So keep that in mind, that most of the time when we're talking about the direction angle, we want it to be positive. Alright, so for part A of this, what we want to do is we want to find the magnitude of our vector based on it having an x component of A and a y component of B. So we're simply going to use the Pythagorean theorem or the distance formula, whichever way you want to think about it. So it's just going to be a squared plus b squared. So there's our magnitude. And then for part B, how can you define a relationship between A, B, and theta? Well, B is the opposite side and A is the adjacent side, and we know those two sides of the triangle define the tangent ratio. So we've got that the tangent of theta is equal to B over A, which means that theta would be the tan inverse of B over A. Alright, so this is how we would calculate the direction angle. And I want to caution you also, make sure that you are aware of what quadrant you're in, because your calculator typically will only give you an answer in the first or the fourth quadrant, and you may need to interpret that if you're in the second or the third quadrant. And then also, since it will give you that answer in the fourth quadrant, it's going to give you the negative angle, so you'll have to subtract the absolute value from 360 to get the positive direction angle. Alright, so let's take a look at a couple quick examples. We want to find the direction angle for each vector, and usually I'll start with just a little sketch. Doesn't have to be too accurate. So here's 4, here's 5. So here's my vector. This would be my direction angle, so we're in the first quadrant. So I know theta is going to be the tan inverse of B over A, so that would be 5 over 4. Make sure you're in degree mode since we want our answer in degrees for these, and you should get 51.34 degrees. As usual, pause the video anytime you have a question, and make sure you write those questions down so that you can ask me the next time you see me. Alright, let's move on to B. We've got 2, negative 5, so here's 2, here's negative 5. Alright, so my direction angle is going to be over here, and the calculator is going to give us this part. So like I mentioned before, we'll have to subtract the absolute value from 360. So theta is going to be the tan inverse of negative 5 over 2, and that should give us negative 68.2 degrees. Therefore, our direction angle is going to be 360 minus 68.2, or 291.8 degrees. Okay, in addition to writing down those questions, let me know if you think there are any errors in the video. Alright, so that's a couple of quick examples on how to find direction angle. Again, be careful if you're in the third or fourth, or second or third quadrants, because you may have to interpret your answer from the calculator. So let's take a look at a couple of examples, and in these examples we're going to look at some other concepts. We're going to look at finding the component form given the magnitude and the direction. Okay? So we are out in a flat desert and a projectile is shot at a speed of 50 miles an hour at an angle of elevation of 30 degrees. So basically what we've got here is 30 degrees angle of elevation, and this number here gives me my magnitude. Alright, that's our magnitude. And the 30 is going to give us our direction, so I know this is a magnitude of 50 miles per hour. And we want to give the component form of the initial velocity. So really what we want to do is we want to find the x component, I'll call it A, and the y component, I'll call that B. So the component form of this vector, just using a little bit of right triangle trig, we could figure out that A is going to be 50 cosine of 30, because I know that the cosine of 30 degrees is equal to A over 50. So if I solve that for A, I would get that A is 50 cosine 30 degrees. And then the sine of 30 degrees would be B over 50. So if I solve that for B, that would give me my y component. That's going to be 50 sine 30 degrees. And 30 degrees is pi over 6. And I know that my coordinates at pi over 6 are root 3 over 2.5. If it is a special angle, I want you to answer in exact form. So then this is going to be 50 times root 3 over 2 and 50 times 1/2. So then the component form of the initial velocity v is going to be 25 root 3 is my x component, and 25 is my y component. Moving on to example 2. Find the component form of a vector that represents the velocity of an airplane descending at a speed of 100 miles per hour. So again, here's my magnitude, at an angle of 30 degrees below the horizontal. So this could be 30 degrees below the horizontal over here, or 30 degrees below the horizontal in the third quadrant. But then they also tell us which is 210 degrees from standard position. So then we know 210 degrees, it's got to be 30 degrees below the horizontal in the third quadrant. Okay, so again, we want to find the component form. And really my reference angle here is 30 degrees. So I know and I'm in the third quadrant, so I know my coordinates again are going to be root 3 over 2, negative, and negative 1/2. So then my component form is going to be my magnitude, which is 100, times the cosine of 210 degrees. Which, again, I just used a reference angle of 30. And 100 times the sine of 210 degrees. So I get 100 times negative root 3 over 2, comma 100 times negative 1/2. And we get negative 50 root 3 for the x component, and negative 50 for the y component. So these are the x and y components of our vector. Alright, moving on to number 3. This is a pretty typical vector problem that you might also see in physics. And we'll see a fair number of these. So we have a force of 600 pounds is required to pull a boat and trailer up a ramp inclined at 15 degrees from horizontal. Find the combined weight of the boat and the trailer. So I'm just going to represent the boat and trailer with a big box here. This is our boat and trailer. And I know that we need 600 pounds of force to keep that from sliding down the ramp. Okay, it's not going to go down, it's not going to go up, it's just to keep it. So we have a couple of forces acting on this box. The first force is the force of gravity. I'm going to call this W for the weight. Alright, so basically what we want to do is we want to find this force of gravity, which is equal to the weight of the boat and the trailer. Then we have a friction force that acts perpendicular to the incline. Alright, and then lastly, we've got that 600 pound force, which is holding the trailer and the boat in place. Alright, so we've got these three forces. We know that the ramp is 15 degrees. And if you notice, I have a big right triangle here. I also have a little right triangle here. And since these two right triangles are going to be similar, I know that this angle here is also going to be 15 degrees. Alright, so I have a little right triangle in here with an opposite side of 600 and a hypotenuse W that I want to find, and I can simply use right triangle trig to find that hypotenuse, which is the weight of the boat and the trailer. So I've got the sine of 15 is equal to 600 over the weight of the boat and the trailer, which means that the weight of the boat and the trailer is going to be 600 divided by sine 15 degrees, which is about 2,318.22 pounds. Okay, so if you have some questions about why these two triangles are similar, make sure that you ask me in class. But basically it has to do with the fact that this hypotenuse here is parallel to this 600 pounds here, and then we end up with some alternate interior angles, and they have the right angles in common, and we can use our, if you remember your no choice theorem from geometry, we can get those triangles similar. Alright, number 4, we've got another incline problem. This time we're given a diagram, so we've got a 200-pound box. So this time we know that this vector going straight down, that force of gravity, which is the weight, is 200 pounds. And again, this triangle and the whole big triangle are going to be similar, so since that's 24 degrees, I know that this angle over here is going to be 24 degrees. And a rope is tied to the box from a post at the top of the ramp to keep it in position. Ignoring friction, how much force is being exerted by the rope? So this is actually the force of the rope. We'll call that vector RQ. Alright, so basically we want to find vector RQ. Again, we have a right triangle trig problem. The RQ vector is the opposite, the 200 is the hypotenuse, so again we're going to use sine. Sine 24 is equal to RQ over 200, and solving for RQ we get 200 sine 24, which is about 81.35 pounds. Alright, so I'm quickly approaching the 15 minutes for this video, so I'm going to stop it here. If you have any questions, make sure you ask.